Hi, everyone. So let's say that we put some pentane in a sealed container. Now, pentane is a liquid at room temperature, so we have this liquid here. But over time, some particles in that liquid will vaporize, turn it up into gas. And so eventually we will get to some point where there is a certain amount of pentane in the vapor phase. And we'll reach a point of dynamic equilibrium where we'll be at the point where in a given moment there might be a certain number of vaporizations, say 3 here, and there are enough vapor particles up here that they can hit and join with the liquid. They can condense at the same rate. In a given moment, we might have 3 vaporizations and 3 condensations. We have equal rates of forward and reverse directions for a process. And so, if we have this condition, then in the next moment there won't be any more or less gaseous pentane because we gained 3 and then we lost 3. There's no change in that amount. And so at this point of equilibrium, the pressure of the pressure on the wall that comes from this vapor will now be constant at this temperature indefinitely. So you can do studies and show that at 25 degrees Celsius, pentane, C5H12, has a vapor pressure of 0.67 atmospheres. But if you were to do a similar test on hexane, which is slightly larger, C6H14, you would see that at that same temperature, there's much less vapor. This is because particles are not as easily able to vaporize because there's a greater attraction between hexane and hexane molecules compared to pentane and pentane molecules. With greater mass comes greater dispersion forces. And so because there's maybe only one of these molecules vaporizing in a given moment, in order to reach that equilibrium, there needs to be only one condensation in a given moment. And so that equilibrium can be achieved at a much lower number of particles up in the vapor phase, at a much lower vapor pressure. And so we can see that for this pentane, which had a weaker attraction, there was a higher vapor pressure. And then for the hexane, which had a stronger attraction, there was a lower vapor pressure. As the strength of intermolecular forces increases, the vapor pressure for a given temperature will decrease. There's lower vapor pressure for particles that have stronger attractions. But you can adjust the vapor pressure by changing the temperature. Take that hexane and now increase the temperature, and now particles are shaking more. They're able to shake free from each other more out of the liquid and turning into gas. You might now have 3 times as much vaporization, and so the vapor pressure will increase until the point where you have enough vapor that it will now condense at 3 times per moment as well. In order to kind of counteract that increased rate of vaporization, there needs to be more vapor particles to have an equal rate of condensation. So we can see that by increasing the temperature, there's an increase in the vapor pressure of that hexane.